So welcome to the lecture, another lecture on statistical machine translation. And today we're going to focus on the standard model these days. Everybody uses it today. It's called the Transformer model. And I decided to merge this lecture with another topic, and that's a topic on including syntax in neural machine translation. You will see at the end why I think the transformer is so closely related topic to that. There's a typo in the title, so I'll have to change the slides. It's syntax in neural machine translation, which is part of statistical machine translation anyway. But we'll start with the transformer architecture. So today, first, I'll briefly remind you what the sequence model was, when it was echoed with attention. Then we'll go in detail over the transformer architecture, and there we'll focus on what is most important components, and that's the self-attention. And then we'll move over to explicit syntax in neural machine translation. And we'll cover multiple ways how that information can be added to neural networks. So we'll be using syntactic information for the network structure, or we'll be adding it to each individual token, and we'll also be adding it somehow to the attention mechanism. Because of the diversity of these approaches, there is currently no single way in which syntax could be useful. So there are multiple ways, and depending on particle settings, the training data sizes, the languages in question, the quality of the explicit linguistic annotation, all that affects whether the information will be useful or not. And the results at the end of this talk are fairly interesting because they suggest that transformer network can learn many of these things by its own without any explicit information. Okay, so here is something that we have discussed in quite close detail in the third lecture in the series. If you have a sequence-to-sequence system with attention, what you have at the top is the input sentence. You process the input sentence with two recurrent neural networks encoders, so two recurrent neural networks, one reading the sentence left to right, the other reading the right to left. And then you merge this information, so at each of these positions, you know, or the network has the capacity to know everything about the full sentence, with a particular focus on the current token. And the first half of the state represents the beginning of the sentence up to the current token, and the second half of the sentence represents the tail of the sentence up to the current token. If you use any of these states for the decoder, then the decoder would have access only to the particular word. But as you are translating the whole sentence, as you are producing the output for the whole sentence, you need to cover all the positions. And that's where the attention mechanism comes into play. The attention mechanism is something which is trained and on the fly, then it decides what weight should be given to each of the input positions at the particular decoding step. So the decoder produces the words as we are used to that, one word at a time. And before emitting the word, it will always consider all the source positions, but each of them weighted according to the attention mechanism. So the attention mechanism is now controlling the word order, but also the general flow of the translation. Here it's the same thing represented in formulas. You have the decoder state, which will be gradually containing more and more information about what's been produced so far. You have the encoder state, the bidirectional recurrent networks. Then you have the attention energies, which decide how important each of the states, and you normalize it with the softmax, and you build the context vector, which is aggregation over all the encoder positions given the weights, and then you emit the the final word based on what the decoder says. So the decoder calls out its previous state, the context vector, the last word produced, and it decides what should be the next word. You again do the output projection to the full ocular size of the target language, and then you pick the most probable token, or you some clever beam search over that. Yeah. So let's move to the transformer model. And the transformer model was introduced in 2017 in a paper which was called "Attention is All You Need," and we will see why attention becomes the central component of that. The paper is very succinct in writing, so it's not easy to distill all the workings of transformer model from the original paper. All you have there are these figures which very grossly summarize the equations. So we'll go in some more detail over that now. And many people have done so. I would very much recommend this blog post on Transformer Illustrated. The description is very clear and simple, and I'm actually using the pictures from that because I really like the pictures. If you prefer the other view, the view from equations, then you can also read the paper, annotate it in PyTorch code. So you can directly see how the paper maps into equations in the neural network system, and then you can train it directly. And there is also a popular summarization of transformer features. So, what is transformer? At the high level, at the highest level, it is very similar to it is just an encoder-decoder approach again, but it's already designed from the beginning to be deep. So it's multiple layers, multiple encoders in a row, and the original paper said 6 is the best number, so it's 6 layers of encoders and 6 layers of decoders. You get the input sentence. The first decoder processes it to some intermediate sequence of representation, and then these new words, whatever they encode, are processed by the next decoder, and so on. So the network has the capacity to do very diverse transformations and like information extractions in this process. And then you arrive at the final representation of the sentence, which is of arbitrary length, obviously, and you use this information, the output of the last encoder, as the input to all the decoders, and the decoders start again, like there's again a sequence of these decoders, and each of these decoders gradually refines the predictions of the previous decoder, so the network can produce the final sentence in sequence of gradual refinements. Whatever it finds appropriate. And each of these decoders has access to the information from the encoder. So that is important that the network always can reconsider what the original sentence was. I'm not highlighting that any further. With a network this deep, it is often very important that you keep some linear flow of information in the network, some residual connections. All of these encoders and decoders can be also skipped. So there is always a combination of like processing at that layer or skipping the information, just taking the information from the previous layer. So the network has the capacity to like copy everything without any calculation, but it obviously performs the transformation. So if we now zoom into one of the encoders and one of the decoders, then in transformer there is this sublayers. The encoder has 2 sublayers. The first of them is the self-attention, and we'll cover that in big detail. And then a standard feed-forward network, which just transforms the coordinates. So if you vaguely remember when we introduced new networks in one of the early lectures, we were saying that a feed-forward network corresponds to a transformation of coordinates, and it can do like the skew and the transposition, and then the nonlinearity. So this very simple operation or short sequence of operations is the only kind of processing capacity, except for the self-attention. So the self-attention is a really critical component, and the computation of the computation of the transformation is limited to this simple feed-forward network. Remember, it's 6 times, so it's 6 layers, so it's quite a big network, but you cannot possibly expect to obtain sensible translations if you use only 6 layers of feed-forward network. So the self-attention is something which is critical. The decoder is similar. It also has this self-attention, so it considers what it produced in the previous layers itself. And it also has the standard style of attention that we know from sequence to sequence, so the encoder-decoder attention. So every decoder state attends, considers all the encoder states with varying weight. And then there is again the feed-forward network for some transformation as needed. Now we can add the word vectors. So if we have the input sequence, there is a standard thing. You do some support processing, so you create some support units. Here the words were frequent enough, so they are not support units, they are full words. You have the embedding layer, so you convert each of these parts, one-hot representations of the word, to the dense vectors. Then you feed them to self-attention, and it will be clear from the next slides that self-attention allows every word to consider every other word. So there is like mutual dependencies between words are studied here within self-attention. That is the place where the network can like flow, where the information can flow from any position to any position. You get some intermediate representations. In some sense, they correspond to the positions of the input words, and the residual connections would like highlight that the position 1 remains to reflect information from the word number 1. But this is not needed, or the network is free to move the information anywhere. So if it's important for later processing, the words can be like totally shuffled. So the correspondence to positions comes kind of as a side effect, and it's not obligatory. And then there is the feed-forward network, which actually is performed token by token. So the feed-forward networks, I've already said that they are very simple, and they are even simpler in that they are not talking, like all the words are not talking to each other anymore. It's token-based, so you do the same transformation at every of these tokens. And that is how you obtain the final result of the encoder layer 1. You have the same number of positions as there were input words. Maybe the information has flowed elsewhere, but it normally stays at that word. And then you pass these tokens, these representations, to the next layer of the encoder. So I've said that information can flow from any token to any token. I've also said that the feed-forward layer is applied token-wise. That means that with this description, the network would have no information about the positions of words. So if the words were totally shuffled, if you shuffle the sentences before feeding them to Transformer, it would have the exact same information. And obviously, positions are important for the meaning of the sentence. And also imagine if the same word appeared at 2 positions, then the network would not have any means to distinguish them. So the way of encoding positions in the transform model is kind of surprising at the first sight, at least. The information about where the token was is stored within each of the units. So what they do is they introduce a so-called positional encoding, and this positional encoding are vectors which change with every single token, and like with the index of the token, so that These vectors are what the network can use then to identify whether the word is at the beginning or at the end of the sentence. And these vectors are added to the word level embeddings. So what these vectors are, it turns out that you could use any random vectors actually, and it would work similarly well. So just distinguishing positions, but not specifying their order in any way would be sufficient. But what is actually used in the paper is something which is kind of similar to the Fourier transform style of information processing. So the way you can look at it is that the first element of the vector flips at the fastest rate, and the second bit flips a little bit with like lower frequency, and the third bit with a yet a little bit lower frequency. So depending on which of the elements you look, there you will see how many sine waves are we from the beginning. So that's the way the positional encoding vectors are constructed, and then they are just simply added without any normalization, whatever, to the word embeddings. So the same word, if you have the word cat twice in the sentence, the same word will have the same word level embedding, but it will differ in the positional embeddings. Yeah. So now let's move to the core element of the transformer network. And that's the self-attention. So let's first motivate for self-attention in some way. So we know that we are processing arbitrarily long sequences, and we need to process them with like fixed size parameters, fixed size structure of the network. And the first method that we've introduced with the sequence-to-sequence architecture was the recurrent neural networks. And that is a simple single matrix that converts the input vector to some state representation, and it combines the state representation from the previous time step with the now new token, producing some output and also producing the state for the next calculation. And if you like the way you implement this is then you time unroll it. You put all these matrices after one another in the calculation. So the network is actually as deep as is the maximum length of the sentences that you are willing to process. And the same parameters are reused many times along this path. And that the problem here, and we've already discussed the problem, is that the calculation is like deep over many steps, and you are reusing the same number many times. And reusing the same number in multiplication can very easily lead to either exploding gradients or vanishing gradients. So that's why the clever cells were introduced to avoid this problem of training. But even if you succeed in training, the problem is that you have to carry out the computation one at a time, and so it's like it will take as many steps as is the length of the sequence. If you do not want to pay this linear cost, if you want to access different parts of the sequence quicker, then the traditional device to do that with neural networks or convolutional neural networks. And there you define at how many surrounding positions am I looking at each step. So that's the kernel size. There will be also some strides specifying like that you skip some of the positions, so you can miss some of the intermediate information and look broader. And if you apply this style of processing, if you apply the convolution network in multiple layers, the receptive field, the span of input elements which contribute to the information in one of the positions can be pretty broad. So with a convolutional neural network, you are specifying two constants: the depth of the network, how many layers, and the kernel size, so the breadth in which it explores the network. And these two numbers specify how long sequences or subsequences are processed at a time. And if this receptive field covers the whole sentence, then perfect, you can process the whole sentence in constant time. Constant in the sense not dependent on the number of positions in the sentence. The parameters, the kernel size and the depth are then arbitrary, and they would depend on the type of text that you're processing. It is possible to train a convolutional network, and at the end of the slide there is the citation. There was actually a paper on using convolution networks for translation, aiming at the same thing as the Transformer paper did, but the Transformer was so interesting that people then totally abandoned the convolution approach. So these days, only very few people continue working with convolutional networks, and everybody moved to this self-attention. So we have the problem that we need to process arbitrary long sequences, and we would like to process them in a constant time. And that is what the self-attention networks achieve. They allow to access any position in constant time, so here is the summary of the complexities. Then that obviously comes at a cost. It comes at a cost of more intermediate numbers needed. So the memory needed in computing the self-attentive network is dependent on the square of the length of the sequences. But the number of operations, the actual calculations that you have to do is also n squared. But the design of the network structure is so that all these computations can be run in parallel. So assuming that your GPU has enough arithmetic logic units, so it can do many computations in one step, then you can really process the arbitrary long sequence in one time step. So that's the benefit. Yeah. So how does the self-attention work? We want to aggregate the information from an input which is arbitrarily long into a fixed size vector, and then we want this to be in a trainable way, so that the network itself can decide what is important and what is not at which point. And what we have as the input are only the sequence of input words or input vectors. So the self-attention introduces this concept of keys, queries, and values. And these are just three different views of the input units. And it's up to the network, it's up to the network to decide what should serve as keys, what should serve as queries, and what should serve as values. The way you obtain these keys, queries, and values is that you simply project the input word embeddings with some projection matrices to the queries or keys or values. So there's one matrix which specifies how the queries are generated from the input token, another matrix which specifies how the keys are generated and how the values are then computed. If these matrices would be identical, yes, you could take the whole vector of the word. So it's up to the network to decide what is important. And now, how are these queries and keys and values used? So the idea is that every position, element at every position, will consult or talk to all the other elements in the sentence, and you will compare them in some way. So you are matching every position with every position. And the keys and queries are the inputs to this match, to this comparison. So you simply calculate the dot product between the query vector, which was obtained from x1 with the query matrix, and the key vector, which was obtained also from the same element with the key matrix. And you see how the query and the key for comparing position 1 and position 1, so like self-attention, the word talking to itself, how that is like salient or important, what is its core. And you also compare the word at position 1 with its query 1 vector to the word in position 2, which is the key for the position 2. So this is where the square comes from. You are comparing every position with every position, and you are always taking the key from one and the query from another one. This will give you some scores, and you normalize these scores in some way so that you account for the dimensionality of the vector representation, and then you apply the normalization that we have seen many times before, the softmax normalization. So then you have some weights which indicate how important for the given position 1 all the positions in the sentence were, including the position 1 itself. So maybe sometimes the network will decide that when doing the transformation at this layer, I will preserve most of the information for this word. I will not consider many of the words around. So the self-attention is heavily focused on the current position itself, or position 1 in this example, and only a little bit of information will come from the position 2. So this way you aggregate the information from the whole sentence at every token position to a new representation. So after the self-attention, you have the same number of positions, but each of the positions now can contain information from anywhere in the sentence. And this calculation was constant time, where we were not looping over anything. The looping can be done in parallel, because each of these calculations does not depend on the result of the previous calculation. So that's the main benefit. The self-attention can be done as in matrices. You have the two input words, the two lines of the X matrix. You first produce the corresponding two query representations for each of the positions. You also create the keys for every position, and you create values for every position. And then you match the keys and the queries, normalize it, and these are the weights after the softmax normalization with which you combine the values. And that is how you obtain the intermediate representation. So this all can be done in constant time on a GPU. That was attention of one head. So in the transformer model, this idea of a node or an item in the sequence observing all other items in this sequence is used several times in parallel, and each of these views or considerations of the input sequence is called a head. So we have discussed the processing which is done in one of the heads, and in the standard transform model you have 8 heads, but people try also many different numbers of those. And each head is defined by the matrices that specify what are the keys, what are the queries, and what are the values. So these trained matrices, they are all initialized totally randomly, but they will specialize in the process of training, and some of the heads can focus on what is the preceding word, some of the heads can focus on what is my governor in the dependency part, some of the heads can focus on just the word itself, totally ignoring the rest and letting the feed-forward layer afterwards do the transformation. So it's totally up to the network what to do. Yeah. So this is 2 heads. For each of the heads, you have the weight matrices which specify what the current token is contributing to the key and what is contributing to the value and to the query. Yeah. So again, these heads are totally independent of each other. So you again can do all these heads in constant time, in parallel, and you obtain 8 different possible outputs. Yeah, so this is kind of surprising, or how do we then handle the this 8 times longer output than we were expecting? Well, you do the normal thing. You would just concatenate them and project them to the size that you wanted. So here is the summary of the self-attention. You have the input sequence of representations. At the beginning, these are the embeddings of individual words combined with the positional encodings. At the subsequent layers, this is the previous layer representation. And in the decoder, you do this twice, and once you are considering the self-attention, the previous decoder information, and in the second step, you are considering also the information from the encoder. So we have the sequence of input vectors. You have a predefined number of heads. Each of the heads is defined by the number by the weight matrices that specify what are keys, queries, and values. You compare all the keys with all the queries, and that will give you the weights that you apply to the values, and then you obtain the resulting representation. You have 8 of those. You concatenate them. You have one train again projection matrix, which squashes it to the original dimension of representation. And then the Z, this final Z, can be used as the input for the next level calculation. The self-attention is used 3 times in Transformer. In the standard thing that we would expect based on the sequence with attention is the encoder-decoder attention. So there the queries are previous decoder layers, and the keys are identical to the values. And they are outputs of the encoder. So the decoder positions here have the chance to consult all the input positions, and it's in a way what people say is that the attention mechanism here only uses the similarity of the representation. So the decoder word finds the most similar word in the encoder. So that's the encoder attention. Then we have the encoder self-attention. That is what we have discussed so far. There, keys, values, and queries are actually said to be identical. So there's only one matrix used for all of that. And then the encoder positions attend to all the encoder positions of the previous layer. And in decoder self-attention, you have the very same thing. But obviously there has to be one more trick done. The decoder produces the output one step at a time, and it would be very wrong to look at the words which I have not produced so far. So the decoder self-attention uses masking, and it's all the following positions from the current positions are forcefully set to blank, set to zeros. And that's how this cheating, this looking into the future is prevented. Okay. So this is what the heads can do. And there have been multiple papers studying what the heads look at, what they consider. You can use the attention weights in a similar way that we've used the attention in the sequence-to-sequence algorithm to see where the network is looking. So if you if you consider the layer 5 of the encoder and and you look at one of the heads, and you look at what the head is looking at, what weights it is assigning to the positions when it is producing the representation, the next layer representation for the word eat. In this example sentence, you can see this. The sentence was, the animal didn't cross the street because it was too tired. And arguably, when interpreting this sentence, we as humans have to know that this it refers to the animal. And this layer, this head number 1 on the layer 5 was actually able to figure that out. So, when producing the next layer representation of it, it really looked most, it consulted most the information which is available in the antecedent of this pronoun. So the weights, the trained weights, managed to identify the antecedent of the pronoun. So the network learned how to find the antecedents. If you look at head number 2, the head number 2 just automatically from random weights learned to look at the syntax of the current clause. So this it is actually the subject in the clause. It was too tired, and it is important to know that the subject and predicate fit together, and that's what the second head looks at. So the second head puts most attention to the verb parts of this clause. So you have these two views. Each of these views is important for understanding what it means and like for producing the translation of the sentence, either in the decoder or the decoder. You have to consider these different sources of information, and the multi-head attention allows for that. If you look at all the 8 heads which are there, it's much less clear what the attention looks at. So there are many strange things that are you cannot really explain in plain words, but somehow they contribute to the best performance of the network, and that's it. So we'll have one lecture in one of the upcoming weeks on the representations that are learned by the networks. And this is where we will go into more detail. People have obviously experimented with a number of heads, so there is also a paper which says that many of the weights after the training can be actually proved because they do not contribute too much to the final result. So you can then scale down your network after training, and you can save some of the computation time. But this doesn't change the number of sequential steps because the actual depth of the network is not changed. Yeah. So let's look at explicit information in neural machine translation, and we'll come to the transformer model and the experiments very soon. But some of the early papers are actually pre-transformer, and that's why the explicit information was there more interesting. So how do we add linguistic information in a neural machine translation system? The idea is that you use tools outside of the NMT system as such. You pre-process the input sentences or the training sentences, the target side training sentences with whatever parsers, taggers that you have, and then you need to somehow put this information to use in the neural NMT system. So one way is that you really follow the linguistic structure of the sentence, the syntactic structure, and you construct the network to mimic that structure. And that is very and it is motivated especially by the fact that the recurrent neural networks process the sequence only left to right and right to left. So the information which was far away in this linear order was too far away in the calculation, and the network might not notice. So that's why 3 LSTMs are introduced. Then we'll briefly mention something which is called graph evolution networks. Essentially, this structuring of the network based on the source syntax can be done on the source side only. Another option how to add this explicit information, syntactic or morphological or any other, is to put this information to every token. So we'll discuss how that can be done. And this is kind of similar to what we have done in morphology in statistical machine translation in one of the previous lectures. So it will be factors, like factors of words. and that is the way to put them on the source side of the NMT system. And on the target side, in some way, you have to rely on the multitasking mechanism. So the network is then trained to produce sequences of words, and in addition to that, also some sequences of this additional information. And this multitasking strategy is supposed to help the network in the main task that you are focusing on. So this is like for the encoder and decoder parts, and there is also the attention mechanism, which was made central by the Transformer paper, and you can also somehow equip the attention calculation with explicit linguistic information. So we'll mention two approaches there. So how to make use of linguistic knowledge in the network structure. Obviously here the linguistic knowledge is usually the syntactic pattern, the syntactic structure of the sentence. If you have the plain LSTM or the GRU, so the clever recurrent network units, they only consider the previous token in the sequence. And that can very easily lead to loss of information. If some words are far away from each other and they depend on each other, this learning mechanism may not notice. If we help the network, if we explicitly ask whatever the verb to consider the information that comes from the subject, then we're helping the network to realize that. So the three LSTMs are modified version of LSTMs, and the change is that the previous state information does not come from the predecessor in the linear order, but it comes from the dependence in the tree. There are two flavors of LSTMs, three LSTMs used. For dependency trees, the property is that the order of dependence in the dependency tree, the order of children, is not too important. Dependency trees are used for morphologically rich languages where the word order is much more flexible. So the mathematical approximation of this behavior is to simply sum the memories from all the children. And that will disregard the order, and it will allow for any number of children that the node happens to have in the current parts. Another variant of the three LSTMs is designed to match or reflect the properties of constituency trees, where there is the grammars of constituency trees are designed so that there is often a fixed number of children, that there is ways to binarize these grammars and so on. So the network then, the three LSTM, is constructed to allow for a fixed number of children and not more, and the calculations depend on whether I'm now processing the memory from child number 1, from child number 2, and so on. So the formulas are slightly different for this LSTM cell, and they differ in whether the children can be of any number, and whether their order is important or not. Here's another approach. Some years later, the idea here is that you have the sequence of states from the normal bidirectional encoder, and what the structure adds on top is that you have additional states which are then traversed bottom up and allow the encoder and decoder, allow the encoder to reconsider what it has accumulated in the linear processing. Now, in this second step deliberation, it is following the dependencies that humans found important, because this upper part is made to mimic the syntactic structure of the sentence. So this is less rigid than the three LSTMs because it has the linear backbone, the standard thing that work well in the sequence-to-sequence approach, and in addition to exploits the explicit knowledge. So another requirement specified or provided in the same paper changes the network structure yet a bit again, and here the goal is to allow the information to flow not only from bottom up, from the words to the top of the syntactic parts of the tree, but also backwards. So here from every position you kind of run a long thread which goes up to the whole tree and then down back to the same node. So every node can consider in the left to right bidirectional encoding. It will consider all its predecessors and all its successors. In this encoding, it considers all its governors in the constituency parse, and then it brings the information from the governors back to the node. So that gave some improvements, especially for Chinese to English translation. I'm not showing any numbers here, essentially because I have not done these experiments myself, and I trust only numbers that I create myself. So here is another way of incorporating explicit knowledge into the network structure. And here the graph convolution networks combine the idea of convolution with the idea of designing network structure along the dependency bars. So first you allow for like looking at surrounding words. So you use some convolutional network with the receptive field covering part of the sentence, not the sentence as a whole. But this is parameterizable. So if you make the constants large, you could cover quite long sentences, and that will give you some more compact representation of whatever is important in that part of the sentence. And then you use the dependency tree to flow the information in multiple layers of the subsequent processing. This is the structure of computation is directly designed to mimic the dependency tree. So each position has access to the dependence to heads and heads to dependence. So in the dependency bars, each node depends on some other node, on one other node, the governor, and then some node is the root of the sentence, which is often the auxiliary node. So each node has one governor and an arbitrary number of children, and the calculation respects that. So there's one weight matrix which tells the node how to make use the information from the governor, and there is another matrix, training matrix, which specifies how to make use of information from the arbitrary number of children. So these were examples of approaches that somehow limit the calculation based on the structure that was identified by the pre-processing of the sentence. And now let's discuss approaches which are conceptually simpler. They will mainly stick to the standard sequence-to-sequence or also transformer style processing. And the added information will be added for each individual token. So now the first question is, how do we actually encode syntactic information at each of the tokens? And this is a very old idea. This is idea which dates back to Mark Speedman's combinatory category grammars and CCGs. And the motivation was to reuse the high quality taggers to do the parse of the sentence. The idea of CCGs in the history was that a special set of word level tags was designed, and then a corpus was annotated with these word level tags, and then a parser was trained on that. So that when you get a new input sentence, run this tagger, but it was called a super tagger because the tags were clever, the tags knew about the whole sentence, kind of. Then, based on these super tags, once you find them, you could directly construct the tree. So the super tags are labels, but these labels are not really atomic. They are treated as atomic in these neural networks, but they were designed to have structure, and that structure reflected how that word fits into the rest of the sentence. So this is the way to put syntactic information into individual tokens. You label the tokens with something that describes what is happening in the surrounding sentence. And by the way, this is what the morphological rich languages do by themselves. In Czech, we have many endings of words, and this is a natural way. These endings are a natural way to indicate the relations between words. The super tagging only makes this explicit and uses like formal labels, but the natural language already exhibits this property. So either you, when putting information together, you rely on the sequence, the order of the bits of information, or you change the individual words in some slight way. You like label the words. So this is the word for a cat. Keep in mind, it is used in accusative, which means it is the object of the sentence. So this ending of the cat in Czech, kočku, instead of kočka, the accusative case, is like word level label to indicate the role of the word in the sentence. And the very same thing is done formally with the combinatory categorical grammar. So here the example sentence is, what city is the Taj Mahal in, or where is the Taj Mahal? And when you're producing this sentence, the fact that you should produce the in or should not produce the in, that depends on something which is very far away. The idea with super text is that you can bring this information a little closer. The idea is that the verb, the is, will be the central element, and this super tag for the CCG tag for the is, for the word is, will differ. The CCG tag will encode that this is the is, which requires the preposition, versus this is the is, which does not require the preposition. So the CCG tags kind of encode valency frames. If you have something in the background, the valencies or subcategorization frames specify what word has to be complemented with, and the CCG tags will put this in a compact label. So if we know this CCG tag, if someone tells us that this word is requires the in, then we will know that we need the in. And the network the set of these tags is obviously much smaller than the set of all the words. So the network can make use of this more dense information. So it can learn, whenever there was a verb which required this in, we need to use the in. So it highlights the syntactic information. So here is the CCG text, just to illustrate them. The text is the subscript here, and in the sentence which has the in at the end, you have the requirement for preposition in that CCG tag. So the CCG tag uses slashes to specify that, like, to make me a valid verb, I need to be complemented by a noun phrase from the right hand side, or a prepositional phrase from the left hand side, and so on. So the CCG tags specify to make me a fully saturated element in the sentence, please provide these. So this is the valency information. The word asks for complements, and by knowing the tags, the super tags, you know that you have to produce these additional elements in the sentence. Yeah. So that was a discussion how to put syntactic information at each token. And we have already in the past discussed the morphological information that is already by design, that belongs by design to the tokens. And the way to formalize this with statistical machine translation systems was one of the easiest ways was to use vectors. So these vectors were additional streams of information, if you remember the lecture on morphology. And in neural NMT, vectors can be very easily used on the source side as well. What you do is you simply construct the vocabularies. You have the vector of word forms, and you construct the vocabulary of that, and then you use embeddings. So you embed the word form. You can do the same thing with the other stream, with the stream of part of speech text, with the stream of morphological text, with the stream of combinatory categorical text, and then you concatenate all these embeddings. So your word level embeddings will be a little bit longer. Some of the elements will come from the word form. Some of them will come from the dependency information in the CCG tag, and so on. And already in 2016, Rico Senric and Berhedo have tried a number of such source vectors, and it helped them in English to German and English to Romanian translation. If you want to make use of this information on the target side, you have to be a little bit clever. You have to, as I said, you have to rely on the network fabulating or making up this output explicit information, and during training you will penalize it for not fabulating it correctly, and then during runtime the network will produce not only the sequence of words that you are after, but it will also produce the sequence of morphological text or sequence of supertext or CCG. And you will generally throw this additional information out, but the network, by thinking about the syntax or thinking about morphological categories, has a bigger chance of producing the sentence correctly. So the simple way to use a sequence-to-sequence network to consider multiple target sequences is to interleave these sequences, especially if they correspond to each, if they correspond position-wise. So a student of mine has worked on morphological information approach, and there the translation went from English into Czech. You know that the Czech is morphologically rich, so it made some benefit in some settings to predict independently the lemma and the morphological tag. So that's what he did. He changed the training data so that the network was consuming in English, and it was producing Czech sequences of the tag and the lemma, and again the tag and the lemma. So the sequence is double the length, and the network immediately learns that it should always use the vocabulary of the text on the odd positions and the vocabulary of lemmas on the even positions. So there is absolutely no errors. The recurrent neural network, the people just learns to like interleave these two sequences. And while doing this, interleaving, the information still flows. So it knows what lemmas were produced, and it knows what texts were produced. And this gave us some interesting improvements even for larger settings. Yeah. So this same was also used by Maria in the same year, and there the interleaved information was the CCG text. So the network, before producing the word, considered for itself and said, okay, now I will produce a noun. And then it produced the noun. And then it said, okay, and now I will produce a verb which will require a subject, noun, and an object, noun phrase. And then it produced receives, and so on. So it it always, before making the lexical decision, it made the syntactic decision. And that gave some improvement. Marian also tried another thing, and that was to use multiple decoders. So this is something that we will cover in multilingual machine translation. You can split the network after the attention or before the attention. So simply after encoding, after processing the whole source sentence, you can create multiple target sequences at the same time of varying length. We're using different decoders. And if you use two different decoders for the words and for their tags, then there is a clear risk that these two sequences will not match in length. So you will produce one translation and a parse of a different translation. So that is a risky approach, and that didn't work as this simple interleaving. So what I did with my students some years after that, we retried this approach with CCG text, and we applied it not only to sequence-to-sequence model, but also to the modern transformer model. And we were predicting the target syntax using a secondary decoder, so the sequences of length could differ, or with the interleaving, which makes the output sentences double the length. That's somewhat risky, but it ensures that every position will have the correct number, or well, it does not ensure, but the network is clever enough to make the text and words properly interleave and have the same number of these additional factors for each output position. So as tags, they use the correct CCG text from a parser, random tags, and also a single dummy tag. So we would just say like B, the first word, and B, the second word. So we were only like with a single dummy tag. The vocabulary size of that was just one. Yeah. And the paper is published in the Private Journal of Mathematical Linguistics. It's called Replacing Linguists with Dummies. That's the dummy tag. And you'll see from the results that sometimes you can replace linguistic annotation with the dummy symbol, and you will get the very same score. So this is the sequence-to-sequence, so the recurrent neural network processing. The interesting thing is that if you use the tag, if the vocabulary size is set to 1 for the interleave tag, then the network does not learn anything useful. And we speculate that the reason here is that the network goes for the lower hanging fruits. And instead of learning something complex like translation, which words should I produce now, it just focuses on getting the credit for predicting the single word at the even positions. So it totally ignores, it stops learning at odd positions, and it learns only at even positions to guess, yes, now comes the single label, now comes the single label. So this is like a badly designed training setting, and the network does not learn it. And then for the CCG text or random text or the baseline, which is this is the interleave setup and this is the multi-decoder setup. So we're testing both, and they both come out similarly. Regardless how you produce this secondary sequence, you get to about similar results. These differences are sometimes reported as significant. Yes, they are. So if you use the interleave setup, the random tags come out slightly better than the correct CCG tags, and both of them are better than the baseline. In the multi-decoder setup, where the output length of the sequences can differ, the baseline is again the lowest performing. The CCGs are a little bit better, but if we stop the training a little bit earlier, then the random tags would be better. So how come that the random tags, the dummies, are as useful as the CCG tags? Well, obviously the CCG tags could be just wrong, but they are not. We've tested and they were not too poor. Our explanation is that the CCG tags are too easy for the network to produce, so it produces them as a side effect. But more importantly, it gets one more time step to think about the next word. So by interleaving, with the interleaving setup, the network has an additional layer in the decoder. So it can like think, it can deliberate one more step about the next word and produce some CCG tags on the go. And this increased depth of the network is what it is you again. So that is our speculation, but it could be explored even further. With the transformer setup, the learning curves have a slightly different shape than with the recurrent networks, but the main observation is the same. If you use the boring identical tags, the network fails to learn. So if you give the network too easy a task, it's not going to learn. In a multitask setting, it is not going to learn the interesting task at all. It will optimize for the easy part and not learn anything. And then the baseline is somewhat worse than CCGs or random tags. And here the CCGs count negligibly better than the random tags. Okay, yeah. So that was it. Linguists can be sometimes replaced by dummy tags, and you have to realize that by increasing the length of the output, you are effectively increasing the depth of the network, so the network is immediately more powerful, and maybe the gain is not coming from the linguistic information because the network is producing it as like for free. It's not difficult for it to produce, but the benefit actually comes from something else. It comes from the increased depth of the network. Here's another approach. This is just to highlight that sometimes the syntactic neighborhood can be encoded into the vectors of words, not by using some formal tagging mechanism such as the CCG supertags, but instead by following the syntactic structure using, for example, convolutional neural networks. So here the input sentence is sparse, then this sparse is used for CNN derivation, which will construct complex representations for each token, and these embeddings are like syntax informed, and they are combined with the normal word embedding. So this is again like word factors, except that the factors are not learned. They are learned considering the syntactic structure. So it's a slightly different construction. Yeah. So now let's move to the last part, and that's making use of linguistic information in the attention. I'm going to skip the details of tree coverage in attention. I just wanted to say that there's a paper, at least one, that restricts the way the attention is calculated. So it's like constraining or changing or specifying the network structure in the attention part based on the source syntax, and that helps because it avoids repeating words in the output. So considering this syntactic information in attention calculation in the form of the formulas was beneficial for this English-Chinese translation. I would like to report more in more detail on an experiment that we did. We realized that the attention heads, the self-attention heads in the transformer model are square matrices, and these square matrices can be seen also as the dependency representation of the sentence. So if one of the heads decided to strictly follow the dependency bars of the source sentence, then it would always attend to the governor and no other words. So if the attention matrices were very peaked, if they would be like one hot, then this particular head would strictly follow the syntactic structure of the sentence. And since we can parse the sentence upfront, we can very easily add it to the training objective and penalize the network for not producing the parse with this particle head. So we have source tokens, we have the multi-layer, multi-head transformer encoder, and we constrain the training of the encoder so that not only it's trying to be most useful for the decoder and match the output sentence, but also its head number 1 has to produce the dependency parse of the source sentence. So this is like a soft way of constraining what the network does. Instead of forcing the calculation to follow the syntactic structure of the sentence, we say, do you find whatever way of combining the numbers you like, but make sure to realize what was the structure of the sentence. And we can obviously add this requirement on the representation of the dependency tree at any of the layers. So we try each of them separately. And so the overall picture is that the objective has 2 parts. One is the normal match the cross entropy with the target sequence, and another is that the attention head, one of 8, is representing the dependency parse of the source. So here are the results. It was translation from Czech into English, and we measure the quality of the translation, the blessed word, and we also measure whether this parse, as produced by the transformer, is matching the parse that the parser sent. And it turns out that depending on, so we do get an improvement of the baseline, where the transformer has just the cross entropy objective, and the best improvement is requiring the parse on the layer 1. So if the network is trained so that right after the words, head number 1 considers the dependence of each word, so somehow the network will learn to find what is my governor, and it will learn to find it early in layer 1 already. Then this information, because the output of the head is used in subsequent layers as a normal transformer, then this information really helps. It leads to better translation in the end. The parses that the network produces at the layer 1 are not the best ones. The best ones are actually from layer 4 or 5. So right after the last, right before the last layer of the encoder. So this is also like not very surprising. If the network has more time and more parameters to train before it emits the final parse, it will do the parse better. So if you want if you have to implement the dependency parser and you don't want to implement your ARM, but you have your training data ready, you can use just the transformer module, train it to translate, and train it to predict the parse on the way, and it will quite succeed in that. And it will best predict the parse on the second to last layer. It will produce better translations if it's forced to know the parse earlier, but the parse is not that very. Okay, and then we tried another thing, and this is again the same idea as the replacing linguistic dummies. I think that every experiment that tries to document that linguistic information or any actual information to the neural network is beneficial also has to try some simple baselines with a similar type of information. So here, the dummy parse that we have is the linear parse. We change the dependency trees from the correct ones from the parser to just the linear sequence. So every word depends on its predecessor, and that's it. So this is the corresponding representation of such a simple dependency tree in the matrix form is that the first word depends on the root, the second word depends on the first word, so it's a diagonal. So we are now training the transformer, and we're training it so that it does not produce true bars, but it produces a diagonal. Here are the results, and you see that the results on the dev set and also on the test set, in terms of translation quality, are actually better than when we use true bars. So if we use these dummy bars, if we force the transformer to learn to produce low cross entropy outputs and at the same time to produce the diagonal matrix, obviously it succeeded greatly in producing the diagonal matrix. That was very easy. The precision of that is close to 100%. But it also improved the translation. And here, the real explanation is not so clear. Somehow it helps for the attention matrices to be peaked. That's it. And it's not important whether we make these self-attention matrices peak towards the true bars or towards the diagonal bars. The translation quality is the same or even better with the diagonal bars. So it helps the transformer to know explicitly what is the preceding word. Again, it helps most when this information is learned at the first layer or available at the first layer. But that is sufficient to get the improvement. So to reiterate, if you have a clever idea what information should be used and how that information is beneficial, obviously go try add that information, see the gain in your blast scores, but then replace your clever information with something very simple, a dummy instead of a linguist, and see whether you are not getting the same gain. And if you are getting the same gain, then you have to think back and you are somehow improving just the calculation property, the stability of the training, or the distribution of the weights in some way. So some peak distribution could be better. So you're just improving the numerical properties of that setup, and the additional linguistic information is actually not needed. So that's it. Today we have discussed Transformer as a great replacement for recurrent neural network, and it was in the same year there was this Gehring paper that also considered the convolutional neural networks attacking the exact same objective to speed up the training and processing to make it constant time. It was possible to get comparable improvements with convolutional neural network, but the self-attentive network in Transformer caught all the attention, and all the field moved to the self-attentive network, and everybody is now working primarily on the Transformer setup. Then we have discussed how explicit syntax can be put into use in neural networks, and we discussed multiple options, putting it into the structure, so like designing computation along the syntactic structure of the sentence in multiple ways, or putting it into individual tokens, and if you do these tokens on the source side, you can do it as vectors, as additions of words. If you do it on the target side, you rely on the multitasking approach, and there the multiple tasks can be really with separate objectives, like two separate decoders, each of them producing its own sequence, or you can run these two decoders within one decoder just by interleaving this sequence. Some gains reported in the papers, I haven't talked about the details, but sometimes they are hard to reproduce in a different setting. So sometimes they are limited to the particular language pair or a small data size that was used by the original authors. So that is one thing. So the papers that report some benefits need not generalize well to larger data or other language pairs. Maybe just the researchers were lucky to spot way work the best. But more importantly, dummy information can be equally useful, and we have seen that twice here for the recurrent inventories as well as for the Transformer architecture. We have seen it with producing CCG supertext, and we have seen it also with constraining the attention to predict the parse. If we did not do this secondary experiment, we would say, oh, well, one can very easily improve translation of transformer model by making the attention head to follow the dependency parse. But we did the contrastive experiment and we tried a dummy parse and we got the same improvement, and that made our paper much more boring, unfortunately. So the conclusion from me is that Transformer learns quite easily some syntax for free, because it has the capacity to attend to all the words, and it learns just as much of the syntax as needed. If we constrain it to produce the dependency parse, yes, it can succeed quite well, but it is not too critical for its performance in the main task. Yeah, so that was it. I hope it was clear enough, and we've just made it in time. So thanks for watching, and if you have any questions, put them to the document. Otherwise, see you next week. Thank you.